Okay, geometric sequence applications. By the end of this presentation, you should be able to create a rule for finding any term in a geometric sequence and then apply this to a range of different scenarios. Finding the nth term is given by this rule. How this rule actually works or why it works, we could consider the sequence 3, 6, 12, 24. So note that the common ratio there is 2. So term 1 is 3, term 2 is 3 times 2, term 3 is 3 times 2 times 2, and term 4 is 3 times 2 times 2 times 2. This can be rewritten, I suppose, with the number of 2's that we've got. So 3 times 2 to the power of 1, 3 times 2 to the power of 2, and 3 times 2 to the power of 3. And then note relationships between the term number and the power number. So term 2 has a power of 1, term 3 has a power of 2, term 4 has a power of 3. So the power is 1 less than the term. So it's your original number, your term 1, times your ratio to the term minus 1, so the number of terms, which is, again, how we got those values. Okay, example. So we're asked to find the nth term of a geometric sequence where the sequence is given by this 3, 6, 12, 24, which is that same sequence we just had above. And we're asked to find the 15th term. The strategy says to use the formula, but in order to use it, we do need to know A, R, and N. So I'm just going to write that sequence again. Note that the ratio is, again, 2. So R is going to be 2. A is our first value of 3. And then that means that our general rule is this one here. So that would be our general rule to find the nth term of this sequence. And as in this particular case, we are after the 15th term, we would substitute in n equals 15. That is a calculator question. So 3 times 2 to the power of 14 is a calculator question. And then that gives us out 49,152. Percentage change. So this is a specific kind of geometric sequence where instead of just having a nice little ratio, we might know that we have a percentage increase or a percentage decrease in order to make the next term. So if there's a percentage reduction, decrease, then your R value can be given by 1 minus, and then that percentage divided by 100. Basically, we're converting the percentage into a decimal, and we're going to go 1 minus it. So that's how much we're going to reduce by. Or if we increase, then it's the same, just plussing instead. So 1 plus that percentage as a decimal to give us that ratio. So for example, we're asked to state correct to 2 decimal places the first 4 terms in each of the geometric sequences for the changes given. The first one says we start at 200 and each new term is 4% less than the previous term. Given that we're 4% less than the previous term, we can say that our ratio is 1 minus our percentage divided by 100. This is the same as 96 on 100 or 0.96. First term is A, which means that for each of these subsequent terms, I can times by 0.96, which is what I'm doing over here. So I'm getting out each of my terms, just using my CAS calculator. And then this gives me these results. Now I wanted the first 4 terms, so I'm going to put the 4 terms in, and then that's my answer. Part B, we start at 500 and we're looking at a 12% increase or 12% more than the previous term. Ratio, again, can be written as 1.12 with a starting value of that 500. I'm going to use the calculator again, so 500 times 1.12, etc., to give me my 4 results. An application of this. So we're going to be using the application, or this particular application question has percentages. So as a park ranger, Megan has been working on a project to increase the number of rare native orchids in Wilson Promontory in Wilson's Promontory National Park. At the start of the project, a survey found 200 of the orchids in the park, and it is assumed from similar projects that the number of orchids will increase by about 18% each year. We're asked to state the first term A and the common ratio R for the geometric sequence for the number of orchids in each year. So A is just the first value, so 200 is the original. The ratio is 1 plus the 18%, so 1 plus 0.18. 1 plus 0.18 gives us 1.18. B is find a rule for the number of orchids at the start of the nth year. So that's using our general formula rule, where A is 200 and R is 1.18. So our rule is 200 times 1.18 to the power of n minus 1. Part C, how many orchids are predicted in 10 years' time? So using our general rule, where n is equal to 10, we can actually solve this. So 200 times 1.18 to the power of 9. That's something I'd put into my calculator. And when it's in my calculator, I get out a result of approximately 887, which this has a scenario, so I'd have to write in words. So it's predicted that 887 orchids would be found or alive or whatever in 10 years' time.